Hello my friends and welcome again to my video channel. Today we will continue our work on the SOMMERKAMP FT221 and now we have part 9, correct. And I don't say that we are at the end of this project. When I say it, this transceiver will hear it and we will not be ready in part 9. What happened in part 8? We had a problem with the PLL loop, with the toroid transformer, bad isolation. The new toroid is mounted, and now the PLL locks again as it should. I got a hint from an OM. Thanks Achim for your hint. He told me that there could be a problem with the heterodyne oscillator with the crystals, the crystal generator for the bands, that some of the crystals are not working properly, so the output is a little bit low, which could affect the PLL. So I will check the output of the crystals and see whether we have a problem or not. I do not have indications for any output, how many millivolt it should be, but when they are all identical, then we can assume that it is okay, except to have a problem with one of the transistors or a mismatch. So my next attempt is to go to the crystals. We have it here. Where do we have it? Here, local units, where we have the trimmers and the crystals. So I will connect the scope and to this wire, the red one, the coax cable, is fed to the PLL. There's a PLL unit nearby, from there to there, and red from here to here. We connect the scope and we can see whether we have a constant amplitude all over the bands. Here we have the output. The frequency is a little bit beyond the specification of the scope. Scope is specified up to 100 megahertz. The oscillators are 125. I do not measure it, I only make a relational measurement and we see the amplitude. By the way, there are two frequencies superimposed. The one is the VCO 133 to 137 megahertz and the other one is from the local board 125 and the difference is 8 megahertz. So we have here two frequencies, but we can see when we go through the bands the amplitude is nearly constant. On the higher bands, maybe the alignment I made was only good for the frequency range up to 146. Anyhow, there are no problems and the frequency is also locked. So this is obviously okay. No need for any further repair. Now setting the FM deviation. A deviation meter is connected to the antenna output via an attenuator, and the NF signal, which is demodulated from the modulation or deviation meter, is connected to the scope, so we see what's happening. We have 1 kilohertz signal, 10 millivolt connected to the microphone input. Mic gain is fully clockwise. By the way, it's the older version of the mic amp unit, so there is no setting for the symmetry. And when we switch on the FM signal, I have to start it again, not to lock onto the Okay, the microphone gain shouldn't be set too much. Center setting 12 o'clock is also okay. We have 5 kilohertz deviation now. 15 kilohertz range. We have also 5 kilohertz, but the signal, you see, the demodulated signal is a little bit distorted. When we reduce the gain, microphone gain, we have 4 kilohertz now. Then the signal looks good. when we set it to 5 kHz as described in the manual, the signal is distorted a little bit. Can't be made better. Again, this is obviously the old version of the microphone amp unit, but I think for FM it is not so important. We have 5 kHz. When we go down to 3 kHz, no problem. That's good enough. Now we will check the 10.7 MHz internal oscillator in mode FM, transmit. The counter is connected to the output of the mic amplifier, to the 10.7 MHz output. Counter is connected. When we go to transmit, we can see the frequency is 10.700 something. That's good enough. I do not try to align it. It's very touchy, very sensitive. I have seen it is not relevant. We are 270 Hertz. A little bit too high, but this is not relevant for the purpose. We have seen that it's not possible to reach the 5 kHz deviation with a frequency of 1000 Hertz modulation frequency. But when we reduce the frequency a little bit, then we can reach 5 kHz deviation and a little bit more. You can see it here, and also amplitude. So we have now more than 5 kHz. This means we have 831 Hertz modulation frequency. This means that with decreasing frequency, the deviation increases. The microphone amplifier is obviously limited in the frequency setting, and when we increase the frequency, we can see we have 4.2 kHz deviation. So that's okay. No further action needed. Aligning the SSB carrier frequency, it's necessary to connect an AF modulation signal from generator to the input, set it to USB, connect a power meter to the output, and the frequency of 1 kHz. We should have 10 watt, so the mic gain can be reduced a little bit, and then we decrease the frequency down to 350 Hertz, and it should have now 2.5 watts or similar. Okay, it's a little bit less. Not as easy as thought. We should make a counter check at 2600 Hertz. Okay, the frequency linearity isn't the best, but we can reach 2600 Hertz. Yes. Maybe the ALC has an effect. We have seen that the output power is much more than 10 watt. So I think it's okay. Mode LSB, We check the same. The linearity of the microphone amplifier isn't the best, frequency linearity, but I have no better idea, so this is as it is. Well, that's it. I checked it before with other alignment mode during the receiver test. It was no, not there, not there. Carrier balance and frequency set. Here we had it. Okay. The CW carrier frequency is first aligned in the mode USB, and then a signal is transmitted. I will do it with a 1 kHz microphone signal and have here monitor receiver. The monitor receiver is needed to have a reference frequency. And then the AM signal is generated but without modulation, so we have only an AM signal, a carrier. I will remove the connector, and then you should hear a tone approximately 800 Hertz, which is okay. This means the carrier oscillator for CW is well aligned and needs no further alignment. We check now the repeater offset 600 kHz in FM mode. The counter is connected. When you switch on, we have 145.500. And when we switch on the repeater function, not reverse, the normal repeater function, then we have 144.900 and 170 Hertz. I will try to improve it a little bit, but as I know, these trimmers are always very touchy. Okay. Switch it off. 500. This is mode in normal. In receive mode, the transceiver is set to 145.500. Repeater mode is switched on, but we still receive on this frequency, because in case of repeater mode, the transmit frequency is shifted down. When I switch to reverse, the signal disappears. When I switch to reverse, the signal should be received on 144.900. Here we have it. Switching back to normal, the signal disappears. This shows us the switching between repeater and non-repeater mode, and reverse and normal is okay. Tone burst unit for the 1750 Hertz tone for repeater operation. We have to remove a bridge, this one, which makes it possible to generate a constant signal, constant 1750 Hertz signal, not only a burst, because this unit only produces a burst for approximately 1 second, which can be set by the pots here. Two other pots are there. One is for the frequency, and the other one is for the output. So the bridge is open, and we can insert this unit into the transceiver and align the frequency. We have the deviation meter again. The output and AF output is connected to the scope and the counter. The deviation is 3.5 kilohertz as it should. We have a higher frequency, 1750 hertz, therefore the deviation is reduced to have a constant bandwidth. And the frequency 1700. That's the right one. Okay. It's rather touchy. But and 3.5 kilohertz, that's okay. And now we will check the duration of the output, pulse of the burst. But for this purpose we have to resolder the bridge, as we have seen. And now a nice question: how is the burst triggered? There is no switch. The microphone, it's not the original one, but this microphone also has no switch. How can the burst be triggered? Well, it's necessary to have it in repeater position, and then listen to the receiver. Nothing happens. And to generate the burst, it is necessary to trigger the PTT twice. You heard it? Nice feature. No knob, only using this PTT knob twice. And when it takes too long, nothing happens. Shorter. Well, nice feature. It's a second, it's okay. I don't change it. Checking the Vox. Brought a problem. This microphone is not good for Vox operation because the coil of the microphone is not connected directly to the transceiver. It's connected via the switch, via the PTT switch. This white wire to the orange wire, and then it is fed into the transceiver. This means when the PTT is not activated, that this coil is not connected to the transceiver, and therefore the Vox cannot operate. Only in case of transmit, when we operate the PTT, then these two contacts are closed, and then the microphone signal is fed to the transceiver. This means when we want to use such a microphone for Vox operation, it's necessary to bridge the contact, which is here normally open in this case, so the microphone signal is fed directly to the transceiver. Why this is made, I don't know. I assume it's made for transceivers where the microphone signal, the inductivity of the coil is used to switch to transmit. Anyhow, for this transceiver it's not necessary because we have a separate PTT contact. So I made this bridge, and now the Vox can be checked. We are in mode FM. The delay can be adjusted a little bit shorter. Okay. There's a trigger point which has to be set. It's the bias for the circuit which is necessary, so we have to set it. to reduce the bias. Vox gain also is effective. And when we turn the Vox gain down to 0, not into the max operation, only down to, then the Vox is not operating. Okay, it works. Checking the CW side tone level. Key is connected. The pot is a little bit down. We need a long isolated screwdriver. That's the output. And now I can set the speaker is connected, the internal speaker. Okay. Checking the Vox circuit again. Okay. Can be set. Only the anti-Vox, which prevents triggering of the Vox by the internal speaker, is a little bit difficult to set. So I think the whole Vox circuit isn't the best. It should be used only together with a headphone, with a headset, and not with a hand mic and the internal speaker. But in general it works, so I can say it's okay. One mechanical problem, you know, these fasteners there, the grommets, they're always broken in old radios equipment because they are a little bit high, and after many years they are decapitated when moving another equipment over it. I tried to find a supplier. I found one. It's a company called Southco. They have such plungers and grommets. Plungers and the grommet. But they don't sell to private persons in low number. And there's a shop in the US, but they don't send it to Europe. So I couldn't pay it, buy and pay it. I was looking for another solution and I found it. The automotive business has similar fasteners. These are such plungers. They are available in different sizes and different versions. And they have a screw which is fed into it. This is the 8mm version. These fasteners are used for fixing any carpets or decorations inside cars, in the trunks, dashboards, bumpers and so on. So these are good replacements. They have the advantage that they're a little bit more flat on the top. Disadvantage, they are a little bit long and we have to look for the size of the hole. It's 8mm, that's not a problem, but maybe the depth is a little bit too high. In this case it's okay, we can use it. They can be screwed in with a screwdriver. That's easy. And then they can be taken out the same way. And you see it is flat, and when there is another equipment sliding over it, nothing happens. That's an alternative solution and I decided to use it. The alignment of the SSB balance in case of transmit has to be done now. We have it set to LSB. Output is connected via an attenuator to the analyzer. There we see, okay, there is still a signal. There are two trimmers, a resistor and a trim cap, which have to be set for best carrier suppression. We will do this now. It's a little bit tricky. They are depending upon each other. Okay. The trick is you have to move the setting of the resistor or the capacitor a little bit above the best point and check it on both sides. Okay. By the way, the top line is 10 watt. It's 10 milliwatt or 10 dB. And we have 30 dB attenuation. USB, LSB, I think that's the best point. Okay. We can leave it in this position. Measurement of the sensitivity of the receiver in mode SSB. There's a manual in translation in German language. It says 0.1 microvolt for 10 dB signal to noise. Don't believe it. There's another manual in the net. It says 0.5 microvolt. I also don't believe it. It's too bad. I set it to 104.5. This is no signal. True RMS meter in the output of the loudspeaker. Same picture on the scope. And when I switch on the signal with 0.15, yes, 0.15, a little bit more than specified 0.1. We have 10 dB. This is 0 and we were on minus 10 dB. This is noise alone. Okay, I should reduce it a little bit. And then I switch on the signal and then we have 0. So now we have signal plus noise. And in the other case we had only noise and the difference is 10 dB for 0.15 microvolt in SSB. Same in mode FM. With no input signal we have some noise set to 0 dBm. It's not specified how it should be measured. It only says 0.4 microvolt at 20 dB sinus. Okay, I will do following. I simply have the noise, and when I switch on the signal with 0.4 microvolt, then the signal drops 10 dB and I add another 10 dB measurement. Sorry, this direction. So we are roughly precise in the range of 20 dB. I could try to reduce the... Okay, I think 20 dB FM is also fulfilled. In mode AM I use a modulated signal. You can hear it. 1 kilohertz and nearly 100% modulation degree. Yes, 80%. And the level is 0.8 microvolt. It should be better than 1 microvolt. When I switch it off, we can see the signal drops much more than 10 dB. so the sensitivity is much higher than the specified 1 microvolt. Totally we can say if this receiver works as it should. It's of course not the most sensitive ones in the world, but for its age, and when we would use it for DXing or so, we would need a preamplifier directly on the antenna, because the loss in the cable would be too high for good reception. For DXing, for local purpose, it's okay, but for DXing we always need an amplifier directly at the antenna. Checking the S meter setting. The S meter is rather sensitive. Signal of 10 microvolt indicated with S9. Okay, there is no option to install the or to align the sensitivity. Only the 0 point and the RF gain and so can be aligned, but not the, for example, S9 position. There is no option in the manual, in the alignment procedure. S meter calibration is not described with a specified input signal, only that it is 0. Okay, 10 microvolt, it is as it is. Project is finished. The transceiver works. We checked it, we aligned it, we repaired it. Looks pretty good. For its age, it's more than 40 years old. It's from the late 70s. The handle is okay. I added the 2 informations regarding nominal voltage. There's a label 230 4 volt AC. It's 2 times 117 volt, and the fuse is 1 amp. Medium blow. Side panel is also okay. Button is okay. These are the feet. Well, that's it. This is the end of this project. It was a long, tough project. One of my longest and toughest projects, maybe except of the Drake TR7 transceivers. But this one also was very challenging due to unexpected and very crazy faults I've never seen before. We had some modification. The meter circuit was modified for unspecific output. I think it was for an indication, maybe for a white sticker. We had a different PLL version. The board was not the original one. And we had a problem with the RF pod. The RF pod was used to make a workaround around the problem on the PLL board. And the problem we found was, as I said, a crazy fault. The toroid core, small transformer, was glued to the board with this famous yellow glue, which is destroying electronics all over the world. Whenever you see such a glue, remove it immediately and check whether the traces, the solder connections and everything beyond it is still okay. In this case, this glue did not be critical due to acid. It was critical because it attacked, or it destroyed the enamel of wires on a toroid core and caused a short. And it took me some time to locate this fault. I never thought that there was a problem. We had a ground connection in a place where there shouldn't be a ground connection. First I thought an IC, the IC 703 is bad, but it wasn't the IC 703 as we have seen. We had a bad diode in the ALC circuit on the bait PA board, and other small topics regarding cleaning switches and so on. The typical problem. I didn't swap the electrolytics because I think they are still okay. I had no indication. I checked optically them all. I took out all boards. I didn't show it in detail, but it was obvious for me that there's no problem. Also, the whole alignment process didn't show any problem. So I think the electrolytics can be assumed as okay. I only swapped one tantalum cap on the PLL board, but the tantalum cap wasn't a problem, as we have seen. Well, I thank you for your patience. This project, I think it is 4 months or so. It was a long delay due to circumstances in my surrounding, not related to my person, but to other persons. So I had a focus in the last weeks and months on other topics, and this is only a hobby for me. So I decided to put it back and focus on more important things. But the situation is cleared now in a positive sense. So I'm sure I can continue with my projects. There are some projects in the pipeline, and I'm sure that I can start them now. Okay, I say thanks. Stay healthy, stay tuned, and see you on this channel.